Okay, good morning everybody. Let's see, should we have to talk business first? Okay, so exam 2 is graded. You should be able to see your grade in Blackboard, and you should be able to click on your exam and see whatever feedback I wrote onto there. If your problem was more or less 100% correct, I just didn't write anything. So it just takes a really long time to do all the check marks on the iPad. So if your exam is blank, that means great, you did a good job. Otherwise, I put comments on there. I really liked all of your responses to the bonus prompt. Some people went with the humorous approach, and some people went with much more serious comments. So appreciate all of that. It really keeps me going while I'm doing all the grading. Okay. So if you're at home, take a minute to pause the video. If you're in person, take a couple minutes in person. Try out these warm-up problems. Just got to do these derivatives here. And then we're going to continue on with our conversation about computing areas under curves. All right, can I have a show of hands for those of you who are finished? Raise your hand, please. Anybody need a little more time? Okay, looks like everybody's done. Okay, so standard derivative warm-up. We've done these a million times. For this one, we're going to need to use, why don't I ask, which rules are we going to need to use to do this derivative of 5e to the 2x? Yeah.
E to the kx.
Yeah, e to the kx rule, multiplication by constant, or if you want to use chain rule, that's also fine. So what is it going to be? We're just going to get f prime equals 5. It's going to float, then we'll just rewrite the e to the 2x and multiply by 2. That's the derivative of 2x, the power. Not too bad. Next one, 2 rules we're going to need. I guess 3, technically. What do we think? ln rule, obviously. What else? Kevin?
Chain rule?
Yeah, chain rule. So we just rewrite 1 over 7x plus 1. That's the derivative of the outside function where I plugged in the original inside one, and I multiply by the derivative of 7x plus 1, which is just 7. All right, last one. Should I use quotient rule? Who used quotient rule on their paper? Anybody not use quotient rule? All right, well then for your instructional benefit, I'll show you how I'm going to not use the chain rule, or I'm going to not use the quotient rule. I'm going to do it by using the chain rule. I'm going to rewrite this as 2 times 2x minus 1 to the negative first power. I'm going to treat this as a chain rule problem where I'm plugging in 2x minus 1 into the equation 2z to the negative 1. If I want to find that derivative, well, the 2 is just going to float. And then I'm going to rewrite 2x minus 1 to the negative second power, and then I'll multiply by 2. So I'll get 4 over 2x minus 1 squared. For those of you who use the quotient rule, did you get the same answer? Anybody get something different? Yeah?
How did you get the negative 2 of x over?
Okay, so actually I forgot to multiply by a negative sign here. I just realized that. Anybody have a negative sign on theirs actually? Okay. You guys gotta catch me for that. Okay, so here's how I did that. I treated this as f of g of x, where g of x was 2x plus 1, or minus 1, and then f of z was 2 over z, or 2z to the negative first power. So when I found this derivative of f prime of z, I used the power rule. The 2 just hangs out. Then I multiply down by the old power, that's negative 1. And then I would take z and I would reduce the power by 1. So 1 less than negative 1 is negative 2. So that's how that negative 2 showed up. Came from the power rule. And then g prime was 2. Okay. Doing those warm-up problems should feel fairly standard at this point, hopefully. If not, then you might want to come to office hours or SI sessions and study up a little bit. Because now we're going to talk about doing the opposite of a derivative, doing an antiderivative. Okay, and doing antiderivatives is a little bit like the first part of the chain rule problems where we wound up doing the opposite of another problem that we were doing, right? For those first parts of the chain rule, instead of taking functions and plugging them into one another, we were supposed to take something which had already been plugged in and figure out what were the original components, right? That was how we started every chain rule problem, by identifying the inside and outside function, and that was kind of a tricky thing to do. And so now we're going to do a similar thing. We're going to look at something and we're going to consider it to be the result of differentiation. And what we want to now answer is, where did we start? If we took the derivative and we wound up here, where did we start? Okay? So an antiderivative is a function. Okay, well, let me be very careful here. I'll say an antiderivative capital F of x of little f of x. Okay, so capital F is the antiderivative and f is the function for which capital F is an antiderivative. Antiderivative f of x is a function f of x such that the following is true. So capital F of x has its derivative is equal to little f of x. Okay, so I guess we write the capital F to signify that it's like one stage up in the sort of integration derivation ladder, so to speak. Okay, so let's have an example. If f of x equals 3x squared, can we find some function capital F of x such that its derivative is 3x squared? Whose function or what function has its derivative equal to 3x squared? Yeah, Kevin?
X cubed.
Yeah, x cubed, right? If I take the function x cubed and I do its derivative, I would multiply down that 3, I'd subtract 1 from the power, and I'd get 3x squared. Now, one thing I want to point out here is the fact that I used the word n here. An antiderivative. I didn't say the antiderivative. Okay, the reason I didn't say the antiderivative is because the antiderivative is not unique. Okay, what does that mean? What that means is there can be multiple functions, capital F of x, such that their derivative are 3x squared, but these functions, capital F, might not be the same. Let's try to think of a function g of x whose derivative is 3x squared, but the function itself is not x cubed. You think of a different function which has the same derivative? Anyone have any ideas? What if I wrote that f of x was the function 3x squared plus 0? 3x squared plus 0. So I did the derivative, and I got 3x squared plus 0. What could I do here, Kevin?
Should you say x cubed plus any constant?
Yeah, we could say x cubed plus any constant. Then that would give us this 3x squared plus 0, right? If I just made g of x x cubed plus 37. Well, if we had capital F and capital G like this, then we would have f prime equals g prime equals 3x squared, right? Because that constant just goes away. Okay, so this is why I say n antiderivative. There's more than one. In fact, there's going to be an infinite number until we kind of nail down a little bit more specific information, right? Because I could just put any number there. I could put 37, 36, 35, whatever number I want. Doesn't even have to be an integer. Okay. So that's what antiderivatives are about. So let's do some practice. Let's try these problems A, B, and C. So let's take a look at 30x to the fourth power here. 30x to the fourth power. And we want to consider some function such that when I take its derivative, I will get the thing in this pink box. Okay, so we got three choices here. We've got f, g, and h. And we're supposed to pick the one which is going to be correct. So let's take a look at capital F of x. 120x cubed. If I take the derivative of 120x cubed, I'm not going to get something times x to the fourth power, am I? No, it's going to multiply down that 3. I'll get 360x squared. So this is how we can check if these are antiderivatives. We can just take their derivative and see if we get the thing that it should be the antiderivative for. Let's try this second one. 6x to the power 5. Well, if I found g prime, it would be 30x to the fourth. I think that's our winner. Let's try the last one just to be extra sure. If we took the derivative of h, we would get 5 times 30, that's 180. Oh, what am I talking about? That's 150. Brain's not on today. Okay. 150, and then x to the power 4. Okay. So it looks like G was our winner here. All right. Why don't you guys try B and C on your own real quick? And then we'll reconvene. Yeah, sure.
That's good, thank you.
Anyone still thinking about it? Does everybody have a choice for each of them? Okay. Let's try B. What do we think for B? Are we thinking F, G, or H? Yeah, Ashton? H. I think H is correct. Let's try it. If we took the derivative of that thing, we would get, well, the 2 would float. Derivative of e to the x is e to the x. And I get plus 0. That does look like what we have there. Let's do the other ones just for fun. If we did g prime, we would get 2e to the 2x. If we did f prime, we'd just get e to the x. So g is wrong because the power doesn't match. And capital F is wrong because there's no 2. All right, how about for c, 4 over x? What do we think an antiderivative for 4 over x is? Kevin?
Is it F?
Capital F, let's try it, do the derivative. The 4 is going to float. And then we get 1 over x for the derivative of ln, which is 4 over x. So Kevin, I think you're absolutely right. When I look at these, the most tempting other option would be g. It looks like, maybe that could have things work out, but let's try doing g prime. We would get 1 over 4x by the chain rule. We would have to multiply by 4 and then plus 0. So we would actually get 1 over x in this case. So that looked like a little bit of an attractive option, but it turns out that if we ever do ln of some constant c times x, the way that this works out is we actually wind up getting 1 over c times x times c, and it's just 1 over x. So if we have ln of 10x, ln of 20x, we're still going to get just 1 over x as that derivative there. And the last one, h, they just put this in to mess with you. I think this looks almost like the derivative of little h. So that would be going in the wrong direction. Okay, we don't want to do a derivative. We want to think about a function for which if we did its derivative, we would get the former function. Okay. So, antiderivative rules and properties of integrals. Hang on, let me make sure that I want to say this. Okay, first I'm going to talk about direct. I should say definite and indefinite integrals. Okay, so here's something that I want to talk about. It's just notation. Okay, notation. An indefinite, no, okay, let me, really want to be super careful saying this stuff. If f of x is an antiderivative of f of x, then we call this thing integral sign f of x dx equals capital F of x plus c, the indefinite integral of f of x, period. This object signifies a family of functions exclamation point. Okay, so let's break down what I'm talking about here. When I write this integral sign thing, specifically this thing on the left, what I'm referring to is all functions for which their derivative is f of x. Okay? So this is going to be a little bit confusing because we just learned that the integral from a to b of f of x dx is the area under the curve from a to b. And now I'm telling you that this is way, 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 way different than integral f of x dx like this. Okay, when I write this thing on the right-hand side, I'm talking about a set of functions. So a bucket where I'm holding every single function that could possibly have its derivative equal to little f of x. Set of functions, that's what's going on here. On the left-hand side, I'm talking about a number. Okay, so these things are very different. So the left, the integral from a to b, we call that the definite integral. And if we don't put our limits of integration a and b on our integral sign, then we're talking about the indefinite integral, which is going to tell us a class of functions. Okay, so let's see what I'm talking about in a little more detail. For example, the way we would write the one we did earlier would be integral 3x squared dx is equal to x cubed plus c. Okay, so what is this statement really saying? The left-hand side says the family of functions whose derivative is 3x squared, and then we have equal sign, looks like x cubed plus c, where c is any number. Okay, that's how this notation is working. So when I see this thing on the left-hand side here, I should think about not a particular function, not a number, but a whole collection of all of the possible functions whose derivative would be 3x squared. Okay? That's just a math notation thing, and students tend to get this notation mixed up very easily with, say, the integral from 0 to 1 of 3x squared dx. And that's going to be some number. It'll be like 1/3. Okay, when we actually compute that. So, maybe I should remind you really quickly what this even meant, the green thing. The green thing means if I have 3x squared, it looks something like this. And here's 1. Then what the green thing is I take rectangles and approximate this area, and I use more and more and more rectangles where I'll use different colors for the different levels, you know, and then I continue using more and more rectangles until my rectangle sum gets really, really close to some number, and that number is what this green box represents. So, definite integral, you get a number. Indefinite integral, we get a class of functions. Class is just like the math word for family of functions, okay? All right, so now I'm going to scroll back up and talk about antiderivative rules and properties of integrals. Okay, we'll do properties first. Property 1. The integral of f of x plus g of x dx. Now, when I talk about the integral of f of x plus g of x dx, am I talking about a number or a class of functions? as a class of functions right now, because we don't have limits of integration. Equals integral f of x dx plus integral g of x dx. So we get something which looks like the sum rule for derivatives, okay? If we take the integral of two functions being added together, it's going to be the same as if we take their integrals and then add them. Okay, next property, well, it's really the same property, but the integral of c times f of x dx, some constant multiplier. We can pull the multiplier out. It's really just a restatement of the first property in a more special circumstance. Okay, and then we'll do rules. Rule 1. There's no particular ordering to these numbers. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. So that should look basically like the power rule. In fact, it's the exact opposite of the power rule. We raise the power by 1 and divide by the new power. That's the opposite of lower the power by 1 and multiply by the old power. Right? Okay, it's like x cubed becomes 3x squared. If we went the other direction, the 3 would float because of property number 2, and then we would have, by this rule number 1, we would have x to the power n plus 1. Well, we go from 2 to 2 plus 1, that's 3. Divide by the new power, that's 3. We would cancel these 3's and we would get that these things are equal. Okay, reverse power rule. What else should we learn? How about the integral of e to the kx dx? Who knows what that's going to be? We're going to have a plus c for sure, but what should come before the plus c? The antiderivative of e to the kx. Give you a hint, we should do the opposite of what the e to the kx derivative rule tells us to do. Kevin?
Divide by k.
Yeah, divide by k. We get e to the kx divided by k. Okay, let's see, is there another rule? Well, there's one more, I think. That was rule 2. Rule 3, ln rule. Integral of 1 over x dx. Well, 1 over x is the derivative of ln, except we got to be a little bit careful here. When we go the other direction, we need to put an absolute value sign here. Okay. Are there any other rules that are really important? Okay, I can't think of any others that are really important off the top of my head. Let's see how much time we got. 15 minutes. Well, let's try... Let's try this problem number 3 real quick. Determine if the following will result in a number or a family of functions. Okay. Why don't we try this first one here. If we take x plus 5x squared dx, what do we think? Number or family of functions? Anyone have a strong opinion? Why don't we do thumbs? Let's have thumbs up if you think family of functions, thumbs down if we think number. Thumbs sideways if you're not sure. Okay, I'm seeing mostly thumbs up for family of functions. It is a family of functions. If I take a family of functions and I add x, well, if I had like x squared plus c, and then I just take that family of functions and I add x to it, then I get a new family of functions. It's the family of functions x squared plus x plus c. All right, how about part C? What do we think? Integral of f of x dx plus the integral from 0 to 1 times 2 f of x plus 2 dx. Same deal. Thumbs up for class of functions, thumbs down for number, thumbs sideways if you're not sure. Okay, I'm seeing a pretty good split here. Some thumbs down, some thumbs up, and some thumbs to the side, which means we should probably talk about this. Okay. Well, it kind of looks like there's three components, or two components really. Our first component is this green thing here. And our second component is this orange guy right here. Now I think we don't see any limits of integration here. So I think we're going to get a class of functions for this green part. So we have a class of functions. And we're adding to that this orange part, which we have limits of integration. We go from 0 to 1, which means that this should result in a number. This will be the area under the curve of the function 2 times f of x plus 2 between x equals 0 and x equals 1. That's what this says. So we get plus some number. So if I take some class of functions x squared plus c and I add to that the number 7, what am I going to get? Number or class of functions? Think class of functions, right? We'll get the class of functions x squared plus 7 plus c. Is actually the same class of functions because we can just change c, right? We could make, by which I mean the class of functions x squared plus c is the same as the class of functions x squared plus 7 plus c, because we could just put the 7 into the constant basically and not worry about it, because c can be any number that we want. So in particular we could make it 7 less than it was before and get the same function. Okay, so class of functions. Basically anytime we see one of these indefinite integrals, we're going to wind up with a class of functions, because if we take a class of functions and we add a function to it, we still have a class of functions. And if we take a class of functions and we add some number to it, it's still the same class of functions, in fact. All right, then down here I think we're going to get a number, because that's a definite integral, and then here we're going to get a class of functions. It'll be the class of functions f of 10 times x plus c by the power rule, the reverse power rule. Here I have a constant. I have some constant times x to the power 0, so if I use the power rule, I should leave the constant. I should make the power 1 more, and then I should divide by the new power, that's 1. So since f of 10 is just some number, if I integrate a number, I will get that number times x by the power rule. So class of functions. Okay, so got 10 minutes left to go over this initial value problem stuff. I know that's kind of a lot of stuff to take in one day, but this is what the schedule demands of us, I guess. So an antiderivative problem with additional constraints can be solved uniquely. Okay, let me write a little bit more and I'll go back and talk about what that means. These constraints are called an initial value. Initial value. So if we have an antiderivative problem coupled with an initial value, then we can start talking about the antiderivative. The particular one that I'm talking about, okay? So it's kind of like I'm being a little bit more specific with what I want from, you know, our function. It's like if I were to look out at the class and say a person with brown hair, you guys wouldn't know who I'm talking about because there are multiple people with brown hair in our class. But if I said has brown hair and is really tall, then you'd know that I'm talking about, well, I guess either Dylan or Sam, probably. Okay? So if I'm more specific, I can narrow it down further. So if I couple an antiderivative problem with an initial value, then I can make it specific. Okay, so let's have an example of what I'm talking about. So this pink thing is our initial value. So they tell us that f of x is some function such that if I take its derivative, I get f of x. And the crucial extra information they give us is f of 1 equals 10. And these two things together are enough to uniquely determine the function capital F. So let's see what should be going on here. Well, we know that f of x is going to be equal to the integral of 2x plus 3x squared minus 7 dx plus some constant c. So let's figure out what c is. Okay? So capital F of x is going to be equal to, well, let's talk about what this integral here is. It's going to be, by the power rule, 2x becomes x squared. Then I get plus, well, the antiderivative of 3x squared, we already did that one. It's x cubed. What does 7 become, or negative 7? If I take its antiderivative. Ashlyn? Yeah, it'll just be multiply it by x. So minus 7x. Okay, plus c. And now the point is, I can figure out what c is by taking this information and plugging it in. So on the left-hand side, I will put 10. And on the right-hand side, I will plug in 1 for x. 1 squared plus 1 cubed minus 7 times 1 plus c. And now I can take this equation and figure out what c is. Okay, so if I subtract over to the other side, minus 1, and then plus 7, same as subtracting 5, I get 5 equal to c. So, looking back at my equation here in green, I know that f of x equals x squared plus x cubed minus 7x plus c, and I know that c is equal to 5 because of the initial value. So my final answer is f of x equals x squared plus x cubed minus 7x plus c. All right? I lost anybody? Ashlyn?
You don't include what C is into.
Ah, I'm sorry. That should be a 5. Yeah, we should definitely make that 5. Now I'm talking about one function, one particular function. It's the function x squared plus x cubed minus 7x plus 5, and there's only one. Okay, if I write a c there, well, since c could be really any number, then I'm really talking about a whole collection of functions. Okay, so that's how I solve this uniquely. Okay, let's see here. Why don't we try some of these problems here? Finding some antiderivatives. Okay, so I want to know what is this. That's really what this question is asking. Find the antiderivative. Most general antiderivative means we're going to talk about a class of functions, family of antiderivatives. Okay, so I know by property number 1 that I can split this up. We can just do the integral of 1 over x plus the integral of 2 over x squared dx. Let's handle the first one first. What do we think for an antiderivative of 1 over x? Some function such that the derivative of that function is 1 over x. Yeah, ln of x. Got to be a little careful though, we need the absolute value sign. Okay, plus c. Plus, now we find an antiderivative of 2 over x squared. Should we use the ln rule again? Or should we use a different rule? Ashlyn?
Would you use e to the kx?
Not e to the kx, but there's another rule that I should use instead of the ln rule. What was the other one we learned? We had e to the kx and ln and the integral of constant times a function. That was one of our properties. The other rule we learned was the power rule. Can we use the power rule here? Yes, we can. We can rewrite this as integral of 2x to the negative 2 dx. And then we could write this as ln of absolute value of x plus c plus raise the power by 1, divide by the new power. That's 2x to the negative first power, and divide by the new power, that's negative 1 plus c. So we get ln of absolute value of x minus 2 over x plus c. Okay? Notice that I actually had two constants here, this c and this c. Okay? But I'm not going to write 2c here because each of these c's can just be any number that they want to be. So if we take two numbers which are not necessarily the same and add them together, I'm just going to get some other number. And depending on the numbers I pick, I can get any possible number by multiplying them together or adding them together. So for example, you could call this C1 and you could call this one C1 and this one C2 and then this one C3. Well, C3 is just going to be C1 plus C2, some other constant. Okay, so that's why I'm just writing one C here. I'm absorbing all of the constants into one term. Okay, so that's how we do that one. Okay, it's 10:30, so I guess we'll stop. If you want to see another example, you can stay after class. Otherwise, I have office hours later today at noon. Oh, one last thing. I have not assigned a new homework assignment yet because I don't think that we've done enough material yet. I'll probably assign a big one that'll be due not this coming Friday, but the following Friday. Okay, so just be aware that you'll have 2 weeks to work on it, but it'll be a little bit longer.
I have a question.
Mm-hmm.
How did you get -1 and then the -1 on the bottom?
Okay, so that came from using the power rule. So when we had 2x to the -2 here, the power rule that we learned on a few pages back said, here, I'll write it on the,
Here.
yeah, so what it said was,
It's right there. Sorry.
yeah, if we have x to the power n, we should make the power 1 larger than it was before, and then divide by that new power. So if you go over to our side, our old power was -2. If we make it 1 bigger than -2, that's -1, and if I divide by this new power, it just goes in the denominator there, it's that -1.
Okay. And then we just find the derivative of that, basically.
So this, to go from here to here, all I did was I said, if I have a -1 power, what that
Oh,
really
just-
means is
okay.
+1 power on the denominator. And then I took this -1 sign and I said, okay, if I take plus a negative, that's the same as doing a minus.
Okay, thank you.
No problem. Yeah, of course. Yeah, so let's try this one. So integral of 2x times 3x plus 7 dx. That's what we're doing. So I haven't really learned anything about how to do the antiderivative of a product of functions. Okay, so I should be cautious moving forward. However, what I could do is go ahead and distribute out this 2x here as 6x squared plus 14x dx. Now I know how to do the antiderivative of each of these terms, and I know that since the antiderivative of a sum is the sum of the antiderivatives, I could just go ahead and do those antiderivatives individually. So how about 6x squared? What's its antiderivative going to be? Okay, so I should use the power rule and the multiplication by constant rule. The multiplication by constant rule says that 6 is just going to float. So I should now write the antiderivative of x squared. What does the power rule say we should do? It says that x to the n should become x to the n plus 1, and then we divide by the new power. Yeah, so it should be x cubed divided by 3 plus 14 times the antiderivative of x. Right now it has a power 1 on it. If I raise that by 1, then I'll have x squared, and then I should divide by the new power. Finally, plus c. If you don't write the plus c, your answer is not correct. So make sure you write it. Okay, so this is a whole bunch of functions. We could rewrite it as 2x cubed plus 7x squared plus c. All right. Why don't we try this one? Integral of x plus 1 over x. Do we know how to do the derivative or the antiderivative of a quotient of functions? We have not learned anything about doing antiderivatives of quotients. So we should do something like we did in the previous problem. We should simplify and try to get it into a form that we know how to handle. How can I simplify x plus 1 over x?
Could you bring x into the numerator and just have it be x to the
No. I think you're right. Yeah. So we could think of this as x plus 1 times x to the negative 1, right? And then we would get, if we distributed that, x times x to the negative 1, what are we going to get? No, I'm just asking, if I do x squared times x cubed, what do I do with the powers? If I want to write this as x to some power, what should the power be? What if I wrote it like this? Okay, so let's review this because this is important. If we have x times x, we call that x squared because x has been multiplied by itself 2 times. If we have x times x times x, we've multiplied it by itself 3 times. We call that x cubed. If we have x times x times x times x times x, we get x to the 5th power.
Oh, I didn't realize what you were doing. Okay.
I thought that was a negative number.
I thought
I was
that was
like,
a
how on
negative
earth
number
is that going to
too.
look like a negative?
Oh, no, sorry. I was trying to make a blank there.
I thought it was negative too.
Okay, my point is we add the powers, right?
Yes.
So if I do x to the power 1 times x to the power negative 1, what do I get?
X to the power.
X to the power of 0. What is x to the power of 0?
Isn't that
1. Now, if I put the x to the negative first power on the 1, I can write that as x to the negative first dx. Okay. You know, the other thing that we could have done that might have been a little bit easier than this would be to say that, well, x plus 1 over x is the same as x over x plus 1 over x, right? Now it's maybe more clear that this should be a 1. Okay, so how do I do this antiderivative? Integral of 1 plus x to the negative first power. Well, I can just do each term individually. What's the antiderivative of 1?
Wouldn't it just be x?
Yeah. Now, how about the antiderivative of x to the negative first power?
would be x to the, would it be 1 over the negative 3? Would you use the power rule?
Well, that's a good question. What if we did use the power rule? If we made the power 1 larger, we would get x to the power 0, and then we divide by the new power, which is 0.
So it'd just be.
Does this seem right? This seems treacherous, right? We know we don't divide by 0, right?
But. No.
So I don't want to use the power rule. There's another rule I can use, though.
ln?
Yeah, ln rule. I think it's confusing you because it's written as x to the negative first power, but if I wrote it like this,
Yeah.
then it's like, okay, now I see that kind of looks like the derivative of ln. So what should come here? I should have a plus c, and what goes in the middle?
And then absolute value of x.
Yes. Very important to include the absolute value sign. Okay, great. So that's our answer for that one.
Thank you.
No problem. You want to try one more?
Sure.
Okay. So we want to do the integral of all this stuff, but let's simplify it a little bit. T divided by t squared, what do I get?
1 over t.
Yeah, 1 over t plus t divided by the square root of t, what do I get?
Would it be t squared to negative? No.
All right, let's review something else then. If I have x to the a divided by x to the b, what do I do with the powers?
Subtract.
I get a minus b. So if I have t to the power 1 divided by t to the power 1/2, and I take those numbers and I subtract them, what do I get?
You just get 1/2.
Yeah, so I'll have t to the 1/2. Right? 1 minus 1/2 is 1/2.
Plus t to the second.
Yeah, plus t squared. dt. Okay, I know I can treat each piece individually. What comes first for the 1 over t, the antiderivative?
Would it be ln absolute value of t?
Yep. Plus,
Would you do plus c?
sure, I mean, we can do plus c for each of them if you want, but why don't we just combine all the c's at the end?
Okay.
So, okay, I'll write plus c, 1, plus, now antiderivative of t to the 1/2 power?
So that's going to be 1, so t to the 1/2 power divided by 1/2.
Yeah, we'll write it as t to the 3/2 divided by 3/2 plus, Jordan, what comes for the t squared?
T squared, that'll be, would you still use the power rule? So,
Yep.
it'd be x, or t to the first power?
No, that would be if we did a derivative.
Okay.
If we do a derivative, the power should become smaller. If we do an antiderivative, the power should become,
Oh, you add, so t cubed over 3.
yeah, t cubed over 3. Okay, plus c3. So we can rewrite all this as ln of absolute value of t plus 2t to the 3/2 over 3
Where'd you get 2?
divided by 3/2 is the same as multiply by 2/3. So that's where that 2 came from. And then plus t cubed over 3 plus, and I'm going to call the constant that I get by taking C1 and C2 and C3 and adding them all together, I'm just going to call that C4. Okay, so I'm just combining all those constants into one thing, because really what this says is if I say take some function f of x and then add to that 3 numbers of your choice, C1, C2, and C3. Well, you adding those 3 numbers of your choice is the same as me adding 1 number of my choice if my choice is the same as the sum of your choices, basically. So Ashlyn says, I like the numbers 1, 2, and 3, and I say, well, instead of doing that, I'm just going to add 6. More questions about these problems?
No, but you said the homework, so we're just going to have a big homework assignment at the end of next week?
Yeah, that's my plan. Because the only thing we really covered that was new last week was Riemann sums. So I'll just do this week and then, yeah. Mm-hmm.
How, how did you get t to? Oh, you just added one. T to daughter.
Yeah, so I took, yeah, so that was when Ashlyn was saying, okay, if we take 1/2 and add 1, we get 1 1/2. I just wrote it as 3/2.
Okay, thank you.
Yep, no problem.